Now we will first start our discussion with symmetrical faults. Okay. So for symmetrical faults, the analysis is comparatively easy because all the phases are balanced. Okay. So what we will take is the per phase equivalent circuits. Per phase circuits we can take and we can analyze. Okay. So first thing that we will discuss is the transients on a transmission line which is unloaded, that is no load is connected to it. Okay. So first we will take a few assumptions. The first one is that the voltage source is a constant source. Okay. So voltage source delivers constant voltage, that means it is ideal, there is no internal impedance, right? And the second assumptions we will take is the parameters of the transmission line, they are lumped parameters and the capacitance is ignored. Okay. So these are the two assumptions that we are going to take. Later on we can analyze along with the impedance of the voltage source. Okay. For now we will discuss only with these assumptions. So now we can draw the per phase circuit. So you have one AC voltage source. So you can take the voltage to be sinusoidal quantity like this. Now this is the transmission line having resistance and inductance. Okay, because we are ignoring the capacitance. So this is R, this is L, and this current is I of t. Here you can take a switch, okay, and there is a short circuit here. Normally it is unloaded, right? Unloaded transmission line. So this switch will be closed when the fault occurs. When fault occurs, that is the instant when the switch is going to be closed. So remember, this is the per phase circuit. Okay, and we are able to take per phase because we are discussing about the symmetrical faults. Okay. Now let us say the fault has occurred. When fault occurs, S will be closed. Now once S is closed, we can apply the KVL. Then what we are going to get? Vm sin omega t plus alpha is equal to Ri of t plus L di of t by dt. So we have expressed in terms of time domain only. We have not made use of the phasors. Okay. Now this is a differential equation. So the solution can be obtained easily only. I am writing the direct solution. Solution of this differential equation is I of t is equal to Vm by mod z sin omega t plus alpha minus theta. Theta is the impedance angle. Okay. So plus Vm by mod z e to the power minus RT by L sin minus alpha plus theta. So you can write here where theta is equal to tan inverse omega L by R. And what is Z? This is the impedance, right? So this is equal to root over R square plus omega square L square, the magnitude of the impedance. Okay. So now this part that you can see here, this is a sinusoidal function, right? It is an oscillating function. Now what about this part? The sine minus alpha plus theta doesn't have a time component. Okay. So it is a constant value with respect to time. So the only function that is variable to time here is the exponential function. So this entire part is going to be exponential in nature. Okay. So for that reason you call this as the steady state part because it is oscillating in nature and it is going to sustain. Whereas this, because it is exponential, it is going to decay after a while, right? It is a decaying function, e to the power minus RT by L. So as t increases, this keeps on decreasing. Okay, so this is a decaying function and that's why it is called as the transient part. Transient part is something which dies off with time. So now this is the total fault current that occurs. Now what we are interested in is to find out the maximum possible fault current. That is, what is the maximum possible value of this fault current. So we will find that out. So why this is important? Because using this only we have to choose the circuit breaker, right? This is one of the factors that is to be considered. So maximum possible fault current. If you see the graph, it will make more sense to you. The sinusoidal part, it is going to oscillate about 0, okay, and the transient part is going to be something like this, right? Now if you add both of them, you're going to get this plus this, and it's going to give you something like this. This is the actual fault current. After a while, normal sinusoidal part will be left out. Initially there will be the transient part, okay. So now what you can see here, the maximum possible fault current is going to be this peak, right? So this is termed as maximum momentary short circuit current, okay. So this is represented as IMM, maximum momentary. Now this value you can visualize from this expression. When you substitute t is equal to 0, this value will be maximum, and the maximum value of this sine part, this is going to be what? Simply Vm by mod z. Now when Vm by mod z will occur when this is 1, right? That means this part should be pi by 2, sine pi by 2, okay. So this maximum value will not occur at t is equal to 0, but this will occur at t is equal to 0. So the maximum value you can see, in fact here also, the maximum value is not exactly occurring at t is equal to 0, but very close to 0, okay. So we can assume this IMM to be approximately equal to the maximum value of the sinusoidal part plus the maximum value of the transient part, sine theta minus alpha, okay. So that's why we are taking the approximation. Now you can also do one more thing here, you can neglect the resistance in comparison to the inductance. So then what will happen, this theta is going to become 90 degrees. So neglecting resistance, we can write theta is equal to 90 degrees. So this gives an even more approximate value as Vm by mod z plus Vm by mod z sine 90 minus alpha is cos alpha, okay. Now once again, at what condition this maximum current is going to be even more maximum? When alpha is equal to 0, right? So when alpha is 0, cos 0 is 1. So in that case, when alpha is equal to 0, then maximum possible IMM will flow, okay. So IMM is approximately equal to 2 times Vm by mod z. So you can see here that it is twice of the steady state part. So momentarily the current can become twice as large, okay. So the circuit breaker should be chosen accordingly. It should be able to tolerate this amount of current momentarily. Now this alpha is equal to 0 means that the voltage, what is alpha here? Here if you remember, we have taken alpha to be the initial phase of the voltage. So alpha is equal to 0 means that at t is equal to 0, the voltage is going to pass through 0, right. So here alpha is equal to 0 is voltage is, or you can take voltage wave because it is a sinusoidal function, right. So voltage wave is passing through 0, okay. And also, like I said, this is the doubling effect, okay. and the circuit breaker must be chosen to withstand this value of current. Okay.